Welcome back to The Explainer. Today, we're setting the stage for Episode 9 of our documentary series, Inside Time Series. We are stepping right into the high-stakes world of business forecasting at a truly massive scale. Seriously, have you ever wondered how tech giants manage to predict user growth, server loads, or advertising revenue day after day with such unbelievable precision? It's this massive, fascinating challenge that takes a unique blend of statistics, engineering, and just sheer computational muscle. So, let's dive right in.
All right, here's our roadmap for today. We're going to cover 1. Forecasting at Facebook scale. 2. Forecasting as building blocks. 3. Inside profit. 4. Engineering business forecasts. And finally, 5. Statistics meets deep learning.
Chapter 1. Forecasting at Facebook scale. Picture this. You're inside a modern tech giant. The sheer scale we are talking about here is mind-boggling. You've got millions of users generating literally billions of interactions every single day. And behind the scenes, there are thousands of specific business metrics that demand daily predictions. Every product team wants forecasts for their daily active users, their ad revenue, their infrastructure demands. Which brings us to our central mystery for this explainer. Why in the world did Facebook feel the need to build an entirely new forecasting algorithm when a proven, classical statistical method like ARIMA already existed? I mean, why wasn't that enough?
Well, it all comes down to the absolute nightmare of forecasting at that kind of scale. Look, traditional models like ARIMA are fantastic, but they're incredibly picky. They require stationary data. They completely stumble when they're missing observations, meaning you have to go in and manually interpolate to fill in those gaps. Plus, in a real business setting, you have constant product changes that rapidly alter your growth trends. You've got complex holiday effects. Think about Thanksgiving or the Super Bowl, which kind of float around the calendar and have irregular impacts. You've also got multiple seasonal patterns overlapping, like a weekly cycle nested right inside a yearly cycle. But the real deal breaker? Classical models required significant manual tuning by highly trained statistical experts, and you simply cannot hand-tune thousands of rapidly changing business metrics every single day. It's impossible.
Which takes us to Chapter 2, Forecasting as Building Blocks.
So to solve this massive engineering bottleneck, the data science team needed a totally fresh approach. Before we get bogged down in the complex math, let's build some intuition about how their solution actually works. The foundation of profit relies on something called a generalized additive model, or GAM. Now, instead of treating a forecast as one giant, rigid, mathematically complex equation that nobody but a PhD can decipher, a GAM is flexible. It breaks every forecast down into independent, totally understandable components. It treats a time series as a sum of individual parts, basically layering them together like building blocks.
Take a look at how Profit literally strips away the noise to show these building blocks independently. Notice these distinct panels. You can clearly see the overall growth trend completely isolated from the rest of the data. Then you see the yearly cycles, the weekly cycles, and those specific shock effects from holidays all modeled entirely on their own. By pulling these components apart, the forecast suddenly becomes incredibly easy for any human being to actually interpret.
Mathematically, this translates to a beautifully straightforward, additive forecasting equation. You've got G for the overall trend or growth, S for seasonality, H for holiday effects, and epsilon for all that random, unpredictable noise. Think about how a massive business event like Black Friday or Diwali directly influences this equation. It provides this huge temporary shock to the H component, but, and this is key, without permanently skewing the underlying baseline growth of the G component. This structural separation, that is the secret sauce.
Chapter 3. Inside the Profit Algorithm.
All right, now that we've got the intuition down, let's pop the hood and see how Profit automates all of this. First up, it uses automatic change points with a sparse prior to automatically detect sudden shifts, like a big product launch, without you having to go in and tweak things manually. For seasonality, it relies on Fourier series. Those are essentially just sine and cosine waves working together to capture smooth annual, weekly, and daily patterns. It uses dummy variables to flag exact holiday dates. And finally, it uses Bayesian inference. This last part is an absolute game changer because it natively provides confidence intervals, which gives business leaders a crystal clear view of the uncertainty baked into their forecast.
Now this is super cool. Notice that diagonal line separating the automated tasks from the human tasks? That represents the complete forecasting pipeline, built on what they call an analyst-in-the-loop formulation. The machine does all the heavy mathematical lifting, the model fitting, generating the forecast.
But because the parameters are human interpretable, analysts can visually inspect the forecasts, spot any weird domain-specific problems, and heuristically adjust the parameters. They can manually add a change point because they know a massive product release is coming next week, effectively injecting their own domain knowledge right back into the automated system.
Chapter 4. Engineering Business Forecasts.
Let's bring this back to the real world and see how this theory maps to everyday engineering challenges, like predicting retail demand or cloud infrastructure capacity. To really understand Prophet's place in the data science toolkit, we need a model showdown. When we contrast Prophet's design choices with ARIMA's limitations, a very clear framework emerges. ARIMA is incredibly mathematically rigorous, and it's absolutely ideal for short-term, linear patterns, but it demands stationary data and very careful manual tuning. Prophet, on the other hand, trades a little bit of that strict statistical purity for raw, robust engineering. It handles missing data and outliers automatically, no manual interpolation required. It trains incredibly fast, we're talking 30 seconds to maybe 5 minutes, and it absolutely excels when your data has strong weekly or yearly seasonality.
Check out this breakdown of recommended application contexts based on empirical studies. If you're forecasting something like interest rates or economic indicators and you have over 200 clean, consecutive observations, ARIMA is often your best bet because of its statistical interpretability. But if you're dealing with retail sales, server loads, or business metrics where you might have minimal historical data, a few missing days here and there, and very strong regular seasonality, Prophet absolutely dominates. It was custom-built for automated business analytics. It's meant to serve engineers at a massive scale, not to completely replace classical forecasting theory.
But, we have to ask, what happens when the data doesn't just have neat seasonal business patterns? What if it's incredibly volatile? Well, empirical studies show that when you're dealing with highly complex, non-linear data sets, modern deep learning models can actually achieve a massive 84 to 87% error reduction compared to traditional classical models like ARIMA.
Which brings us to Chapter 5, when statistics meets deep learning.
Look, as amazing as Prophet is for business metrics, it's not a magic wand. Where does it actually fall short? Well, it struggles big time with highly complex, nonlinear dependencies. If you're looking at extremely volatile data that lacks a clear seasonal structure, I'm talking tick-level financial markets, speech patterns, video, things like that, Prophet's additive building blocks just can't capture the chaos. It also assumes an additive structure natively, so it struggles a bit with multiplicative seasonality, and it is primarily designed for univariate forecasting. That means it looks at one single variable at a time rather than untangling complex multivariable interactions.
When relationships become that highly nonlinear, modern problems require modern solutions. This chart visualizes the root mean squared error, or RMSE, across different models on complex datasets. Keep in mind, lower is better here. You can see ARIMA sitting at 3.11. Prophet improves on that, dropping to 2.85. But look at the deep learning model, the LSTM. It achieves an incredible error rate of just 2.48. Neural networks like LSTMs are uniquely capable of learning long-range dependencies and insanely complex interactions directly from the data itself, without needing a human analyst to go in and manually specify seasonality or holiday effects.
And that leaves us with this really powerful thought to chew on. Classical forecasting taught computers to understand time. Deep learning taught them to remember it. Classical statistics gave us the mathematical rigor. Prophet gave us the hybrid, highly scalable business engine. But machine learning, that is opening up a completely new frontier of pattern recognition.
And guess what? That is exactly where we're heading next. In episode 10, we're going to ask, how did neural networks actually learn to remember the past through long short-term memory, or LSTM networks? We are going to unpack the deep learning breakthrough that changed forecasting forever. Thank you so much for joining me on this explainer of the Prophet mystery, and I will see you in the next one.